The sun is the superpower of our solar system. A thermonuclear blast furnace erupting with massive explosions.
It can be the same amount of mass as Mount Everest coming out from the sun and flying out into space.
At 93 million miles away, it would seem that we're safe from the sun's wrath. But are we?
It matters, especially in modern times, what the sun is doing.
From the center of the sun, as it rotates around, is the kill zone.
With some experts predicting the most violent outbreak of solar activity in modern history, it's never been more important to understand the secrets of the sun. There are billions of stars in the universe, but one alone dominates our cosmic neighborhood: the sun. It's an infernal sphere of mostly hydrogen and helium, superheated into a plasma that burns at millions of degrees. Its surface rages with violent explosions as it spews out storms of deadly radiation millions of miles into space. Our sun is a type of star known as a yellow dwarf. Yellow because of the color of its surface, and dwarf because it's small for a star. But small is relative. Within its boundaries, you could fit 1 million Earths. In our solar system, there's simply no bigger star than the sun. At 1 million miles across, it's a massive celestial blockbuster.
The sun is really pretty huge. It dominates our solar system. Not only is it the biggest star in the solar system, it's the only star in the solar system. It's surrounded by a bunch of smaller stuff that we call planets and comets and moons. But the sun is our star.
Our star is an enormous source of heat and energy. It has a surface temperature of 10,000 degrees Fahrenheit and generates 380 billion megawatts of power. This dwarfs anything on the human scale. Hoover Dam in Nevada only generates 2,080 megawatts. In 1 second, the sun churns out more energy than has been used in all of human civilization. All that power in the blink of an eye. Incredibly, it's been burning this way for billions of years.
Early astronomers didn't quite understand how the sun could generate so much energy for that long a period of time. That was the first mystery, was really how the sun generates its energy.
In the early 19th century, scientists assumed that the sun worked just like any fire on Earth, that there was a source of fuel, perhaps coal, that was slowly burning away. But there was a serious problem with this theory.
I've got a fire in front of me here. If I want it to keep burning, I have to keep adding wood to it. This fire will last maybe an hour, unless I add some more wood. Now, if I had a pile of wood the size of the whole sun, and somehow enough oxygen to burn it, it would only take about 5,000 or 6,000 years to burn out. That's a long time, but it's not long enough to sustain life on Earth.
By the early 20th century, carbon dating of Earth rocks and fossils had proven that the sun was in existence and at temperatures warm enough to sustain life, not for thousands of years, but for 3 billion. If you wanted to build a fire that would last that long, you would need 72 trillion cords of firewood. That's 12,000 cords for each man, woman, and child on the planet. Clearly, there had to be some other process unknown on Earth that was powering the sun. In the 1920s, scientists found the answer to the puzzle in a process that would later be harnessed to fuel the hydrogen bomb: nuclear fusion. Fusion occurs when atoms are smashed together at a high rate of speed and literally fused. To get this to happen, conditions have to be just right.
For any interaction to happen, these two protons each has a positive electric charge, and so they would repel each other. So you've got to get them close enough together. And to do that, it's got to be hot, which means the particles moving very fast, and dense enough that they hit each other and they can get close enough together that they actually fuse.
The core of the sun is the perfect cauldron for nuclear fusion. It's the hottest place in the solar system at a sweltering 27 million degrees Fahrenheit, and it's also incredibly dense.
It's so dense, it's 10 times the density of lead. And you would think at that density it should be a solid, but it's not because it's so hot that it remains a plasma.
If you heat a gas to high enough temperatures, electrons fall off of the atoms and they float around in the soup. And so it has behavior that's different from what a gas would do. And so we have a different word for it, call it plasma.
To truly understand what goes on in the core of the sun, you have to find some way to imagine the almost unimaginable.
In addition to studying the sun, I also play pool. And the sun is a place where there are billions of particles colliding and interacting with each other. And it's really not unlike a cosmic pool table on an unimaginable scale. It doesn't matter how hard you hit a ball. You would never hit it hard enough to actually fuse that ball together with another ball. But there's so much pressure and such high density at the core of the sun that the two objects impacting each other will actually fuse.
In the sun, these objects are hydrogen atoms flung together by immense pressure to form helium atoms. In this fusion process, the resulting atom is slightly less massive than the ones that created it. The missing mass is given off as energy. Each second inside the sun, 600 million tons of hydrogen are fused into 595 million tons of helium. That 5 million tons of mass lost in the process is converted into energy equal to 1 billion 1 megaton hydrogen bombs. That's every second.
When you look out into the cosmos, the process that gives you the highest return of energy for free is what goes on in the centers of stars like the sun.
So we now know that the sun is powered by nuclear fusion. It's the only fuel that we know that can sustain the burning in the sun long enough to sustain life on Earth, billions of years.
Sunlight. It's so central to life that we don't often give it a second thought.